This movie is about multiplication of matrices. How do you do it? The first thing to recognize is that it's not the way you might think. You don't multiply just term by term. -1 times 3 is -3. This is not the way matrix multiplication is done. The reason it's not done this way is because this kind of multiplication doesn't prove to be very useful. Here's a simple example to illustrate how it is done. We have a matrix with only one row, 3 columns, and a matrix with only one column, 3 rows. A 1 by 3 times a 3 by 1 matrix. And that will give us a 1 by 1 matrix, a matrix with only one number. And we do multiply entries term by term, but in the following way. 3 times 7 plus -1 times 4 plus 2 times 1. Total that all up and we get 19. That's the way this row matrix is multiplied times this column matrix. When we go to larger matrices, it's the same way, just to multiply a row of the left matrix times a column of the right matrix, and do that over and over for every possible row of the left matrix and every possible column of the right matrix. The size requirement is the matrix on the left, the number of rows, and the matrix on the right, the number of columns of it, will determine the size of the product matrix. Here we see the left matrix with 2 rows, the right matrix with 3 columns, and the product matrix will therefore have 2 rows and 3 columns. In order for the multiplication to be possible, the number of columns, 1, 2, 3, of the left matrix has to match the number of rows of the right matrix. When you multiply matrices, you're always multiplying a row of the left matrix times a column of the right matrix. Let's do this 2 by 3 matrix times 3 by 3 matrix and see how it works. To determine what goes in the row 1, column 1 position, we do row 1 of the left matrix times column 1 of the right matrix. -1 times 1 plus 2 times -1 plus 7 times 0 is -3. The entry in row 1, column 2 is determined by multiplying row 1 of the left matrix times column 2 of the right matrix. -1 times 2 plus 2 times 4 plus 7 times 2 is 20. The 5 in row 1, column 3 is obtained by multiplying row 1 of the left matrix times column 3 of the right matrix in the same fashion. When we come down to the second row of the product matrix, here we're in row 2, column 1, so we're multiplying row 2 of the left matrix times column 1 of the right matrix. Row 2 times column 2 gives us the 28 in this spot, and row 2 times column 3 gives us the 40 in the row 2, column 3 position of the product matrix. Bear in mind that matrix multiplication is not commutative. In general, multiplying A times B is not the same thing as multiplying B times A. And in fact, it's frequently the case that one of the multiplications is possible and the other one is not possible because the sizes of the matrices don't match up right. Some facts about matrix arithmetic. Matrix addition is commutative. Adding in A plus B is the same as B plus A. The order doesn't matter. Property 2 is called the associative law for matrix addition. If you're adding A to the sum of B and C, it's the same as adding C to the sum of A and B. 3 is the associative law for matrix multiplication. And 4 is called the distributive law. Multiplying A times the sum of matrices is the same as multiplying A times each one separately and then adding. This matrix with 1s running down the diagonal from left to right, upper left to lower right, has a special role in matrix arithmetic. The zeros, it's got zeros everywhere else, but 1s on that main diagonal. And the property of interest that that matrix has is that when you multiply it times another matrix, if the other matrix is of a size so that the multiplication is possible, then the other matrix is not changed. Notice that the product matrix in this case is the same as the matrix that we started out with on the left. You can check that very easily by just doing the multiplication that we've just learned. So the role that this matrix is playing with matrix multiplication is analogous to the role that the number 1 plays with numerical multiplication. The number 1 has the property that multiplying 1 times any other number leaves the other number unchanged, and multiplying a matrix by this matrix that we're looking at has a similar property. This matrix is named the 3 by 3 identity matrix. The 2 by 2 matrix with 1s on that main diagonal and zeros elsewhere is called the 2 by 2 identity matrix. So you can have an identity matrix of any square size, square meaning the number of rows has to be the same as the number of columns. All identity matrices are square matrices. This is an example of matrix multiplication. We have two matrices D and B. The matrix D is a price matrix. It gives the price of a number of different items at 4 different grocery stores. The items are a dozen eggs, a loaf of bread, a case of beer, and a pound of hamburger. For example, the price of a dozen eggs at Food Lion is $1.73. The price of a case of beer at Winn-Dixie is $9.98, and so forth. The second matrix is a shopping list. It says we're going to buy 2 dozen eggs, 3 loaves of bread, 1 case of beer, and 4 pounds of hamburger. What I want you to think about is what you would be computing if you did the matrix multiplication D times B. A 4 times 4 times a 4 by 1. That multiplication works because we have the same number of columns in matrix D as we do rows in matrix B. But what's the significance of the product matrix that we would be computing? When we do row 1 of D times the only column of B, we're saying $1.79 for eggs times 2 dozen eggs, plus $1.95 for a loaf of bread times 3 loaves of bread, plus $10.99 for beer times a case of beer, plus $3.79 for a pound of hamburger times 4 pounds of hamburger. So what we're calculating when we do that row times that column is the price of purchasing the entire shopping list if we're shopping at Harris Teeter. And similarly, when we come down and do the second row times that column, we're calculating the price of purchasing the entire shopping list at Food Lion, and then for the other 2 stores when we do the other 2 rows. So in summary, doing the matrix multiplication gives us the cost of doing the shopping at each of the 4 stores. Now you can take this a bit further. Let's extend the shopping list to 3 shopping lists. Suppose the matrix C shows the shopping list of Ann, and also Bob, who's going to buy 1 dozen eggs, 2 loaves of bread, 1 case of beer, 2 pounds of hamburger, and also the shopping list of Casey. Now when we multiply D times C, for example, doing row 3 of D times column 2 of the matrix C, we would be calculating the total cost of purchasing Bob's shopping list at Winn-Dixie as our choice of store. So the matrix multiplication now would give us every conceivable cost of purchasing any of the 3 shopping lists at any of the 4 stores. A very important thing to notice here is that I have set up the matrices and in such a way that when I'm doing the multiplication, the column labels for the matrix that's going to be on the left when I multiply match the row labels for the matrix that's going to be on the right. Almost always when you're doing a word problem that involves matrix multiplication, you're going to want that to be the case. If you set it up so that your left matrix has column labels that match the row labels of the matrix on the right, then that generally means you're doing your multiplication in a fashion that it's computing what it is you actually want to be doing. So the product matrix in this case, if you do the multiplication and then in your product, I'm labeling the product matrix using the row labels from the matrix on the left. These are the row labels from D, and the column labels from the matrix on the right, which is C. Then I've got the right kind of bookkeeping scheme set up to interpret the entries that I get. When I do the matrix multiplication, for example, the number that goes in this spot right here, row 2, column 3, would be the cost of purchasing Casey's shopping list at Food Lion grocery store. Down here I would have the cost of purchasing Bob's shopping list at Safeway. So let me say that once more. Row labels for the product matrix are the row labels from the matrix on the left. Column labels in the product matrix are the column labels of the matrix on the right.